Thanks, everyone. I'll try to keep it short. The work that I'm going to present today is joint work with my faculty colleague, Manuel Gomez Rodriguez, and my PhD student, Mohammad Bilal Zafar, and Isabel Varela, who is a postdoctoral researcher at our institute. Most of the hard work was done by these people, so I get to present. Let me just, okay, I'm just trying to see how to get out of this. Okay, so I'm going to talk about discrimination in decision making, and in particular, I'm going to talk about human versus machine decision making. So what do I mean by machine decision making, and what do I mean by discrimination? Well, what I mean here is something that we have been talking about throughout the day today. I'm referring to data-driven algorithmic decision making, where we learn over past data, where we use some training data based on past decisions. Now, today, these sorts of decision making is being used to assist and replace human decision making in a whole bunch of different scenarios, from recruiting to banking to judiciary and journalism. I'm not going to go through the examples because you're probably familiar. So I'm going to focus this talk on the concept of discrimination. Now, the first point I'm going to make, presumably it is obvious to some of you, which is that discrimination is a very, very specific type of unfairness. You can have a number of different ways in which your decision making could be unfair without it being discriminatory. Simplest example would be, imagine a dictator who oppresses everybody in a country. He or she is not being discriminatory, but it's unfair. But I'm going to talk about only one type of unfairness, which is discrimination. Now, discrimination itself has been extremely well studied in social sciences. It's a concept that is almost about 100 years old. It has been studied in social sciences, moral philosophy, economics, and there are multiple laws in many countries have anti-discrimination laws. And in fact, discrimination is recognized even in international human rights law. What I'm going to try to argue in this talk today is that discrimination to date has been less studied from a computational perspective. And I'm going to make the case that it is actually important and vital to study it from a computational perspective. Now, why is that? Two reasons. The first one, already data mining methods are being used to detect discrimination even in human decision-making scenarios. For instance, these days, not a day goes by without, when you flip the pages of any major newspaper, you would have some story about some decision-making scenario, which includes human decision-making scenarios, where somebody has analyzed some data sets about human decision making and discovered that there was some evidence of discrimination. For instance, here I'm showing two examples. The first one is some analysis done over decisions made by New York police in terms of who they stop and frisk. And the second one is about Airbnb, people who make their houses available on Airbnb and their choices in who they allow to stay in their homes versus who they don't, who they reject. This is one reason. The second reason for studying discrimination from a computational perspective is because increasingly we need to make sure that whatever we are learning or our learning methods actually avoid discrimination. The previous one was detecting discrimination. This is about avoiding discrimination when you're using algorithmic decision making. Now, at this point, some of you might ask, but aren't algorithmic decisions inherently objective? Isn't discrimination something that is intentional and subjective? Well, unfortunately, objective decision making doesn't by default make them fair and non-discriminatory. In fact, objective decisions can actually be unfair and discriminatory. The reasons are, imagine if your training data actually has some discrimination contained within it, because you're training, say you're learning how to select applicants in a recruiting process, but your training data is generated by humans in the past, and as a result already has some discrimination contained in those decisions. Then your algorithms are going to objectively learn those biases. And the other thing is, oftentimes learning objectives try to make the decision accurate over all the users in the training data. And what this might result is, in certain scenarios, it might result in disparity in outcomes for different subgroups of users within your training data set. So for instance, there have been studies of price discrimination that somehow crept in to the online prices offered by certain websites, in part because they didn't take care to ensure that different subgroups of users were actually being offered similar prices. So our agenda is largely driven by two high-level questions. The first is how to detect discrimination in decision making. And the second one is about how to avoid discrimination when you're learning so that you can make fairer decisions. And the hope here is that if we could do this, then maybe there is, in the long term, there is a potential to eliminate biases from algorithms in a much more easier fashion than actually retraining people to remove their own implicit biases. So in this talk, I'm going to focus only on the second part, which is about learning to avoid discrimination. So let's get into the concept of discrimination. Here is sort of like a first approximate definition. It's sort of like a moralized definition or a normative definition. So I look at discrimination as wrongfully imposing a relative disadvantage on people or persons based on their membership in some socially salient group, for instance, race or gender. Hopefully, this is a definition that none of you have serious objections to, but this definition actually has a number of details that that become quite interesting when we start getting into it. So the devil is in the details. So let's start with the first interesting part, which is what constitutes a socially salient group. Now, race or gender seem to be like obvious choices, but why not start thinking about people based on whether they're bald or whether they're not bald, or whether they're wearing certain jackets of a certain type versus another type? Like, what constitutes a socially salient group? Now, this is often up for debates. In fact, people often start movements and push to include specific types of groups as socially salient groups. Like, for instance, based on sexual orientation for a long period of time was not included in the anti-discrimination laws as a socially salient group, but it eventually was. Second, what constitutes relative disadvantage? It might seem obvious, but sometimes when you're making a decision and it's often the directionality of the advantage or the disadvantages that are conferred by a decision can be quite tricky as well. For instance, when you have segregated education of people based on race, is it disadvantageous to people of one race, or could one argue that it's disadvantageous to people of both races because they're not allowed to interact with people of another race? How do you determine that? There are long standing arguments and disputes about them. An even bigger thing is about what constitutes a wrongful decision. This is a very tricky issue that moral philosophers often debate about. Now, in this talk, I'm not going to focus on any of those three because they're way outside of my domain of expertise. I'm going to focus on this simple phrase in that definition, which is based on. What constitutes based on? And I would argue that this is a question that has to be dealt from a computational perspective. It is a question for computer scientists to answer. Now, to discuss what constitutes based on, let me propose a very simple computational framework for thinking about decision making. Let's consider the simplest form of decision making, which is binary classification. That means you have a bunch of users and you have to decide whether you either accept them or reject them. It's a simple binary classification task, and you have multiple different attributes for these users, and your decision, in this particular case machine, is using this information about users, their attributes, to make the decision. Now, the interesting thing in the context of discrimination is we're going to color the attributes as red or green. The red attributes are the sensitive attributes. Who defined what is sensitive or not? Let's assume that the lawyers and the other people have solved that part of the problem. So the red attributes have to be treated in a special way. The green attributes are the non-sensitive attributes. That means they're fair to be used in whatever way you would want to achieve your decisions. Now, the key requirement for discrimination is that decisions should not be based on sensitive attributes. Now, the question is, what constitutes not based on? Now, intuitively, you would think that the most intuitive notion would be, why don't we just simply ignore the sensitive attributes, right? Let's just cover the red attributes up. Let's make our decisions based on the remaining green attributes, and then we're probably done because we are ignoring it. How could we be unfair? In fact, there is a simple way in which you could do this, which is when you're learning or when you're training your model on that, just strip out. That means just remove all the red attributes from the inputs, train your learning model. It seems to satisfy this simple intuitive notion. In fact, it is a good way of training data. It would avoid what I would call as disparate treatment. And what disparate treatment means is the property that it satisfies is that if you have two users who have the same values for all the non-sensitive attributes, that means who have the same green attribute values, but even if they differ along the red attribute, then they would receive similar outcomes, right? It's a nice property to have. In fact, it would pass certain tests called situational testing, which is often used for detecting discrimination, right? So there is a lot of interesting things that can be done by this very, very simple notion of stripping out the red attributes. However, as you might expect, this is not the end of the talk. It turns out that there are still two important problems with this simple intuitive notion. And these problems actually come up when the different sensitive attribute groups, that means the red attributes, have some correlation with the green attributes. That's when you can have two other types of problems. The first problem is what I'm going to call as disparate mistreatment. Notice that previous one was disparate treatment. I'm now talking about mistreatment. And how it manifests itself is when you take people with different sensitive attribute values, they might have different misclassification rates. And this thing can crop up, this thing can come up even when the training data is unbiased. I will explain in a few slides why this might come up. The other thing is what I'm going to call as disparate impact. Disparate impact comes in when the labels, particularly in the training data, are biased. Stripping out the red attributes is not going to solve the problems. Okay, so this kind of a thing can come up even when the training data is unbiased. This one can come up even, and this one is particularly can come up when the training data is biased. Let me walk you through why these things might come up. But before that, I need most of you, or I mean, if you're familiar with machine learning, this will be utterly obvious. If you're not, if you don't have much of a background of machine learning, just remember these 2 points for the rest of my talk. The first thing is, whenever you're learning, the first thing that we do is we define and optimize some sort of a risk or a loss function over all examples of the data, right? So these are some example loss functions. And what is a typical loss function? A loss or a risk function is something that captures how inaccurate you would be if you were to train your model to optimize, that is, to minimize this loss function. So learning is nothing more than defining and optimizing for some sort of a loss function. And learning is often classed as an optimization problem. That means you try to minimize the inaccuracy or the risk or the loss you have in the function that you define. This is the first point to remember. The second point to remember is that for efficient learning, you would want to have a function that you can solve, that you can optimize for easily. And so typically there is a class of functions that are called as convex functions, and you often define a loss function to be convex because it enables you to learn efficiently. If you define you can define any loss function, but if it's not convex, you're going to struggle to learn the right optimum value, and your learning will be extremely inefficient. Okay, these are the 2 points to remember. So let's go back to the origins of disparate mistreatment. What is this thing, and why does this come up? Let's go back to the original scenario again. You have the red attributes and you have the green attributes, and let's assume now that the users in this data set are actually from 2 different groups. That is, there are blue users and pink users, and we separate them based on their value of the sensitive attribute. Okay, some of them are blue and some of them are pink. Now, when you're trying to minimize your loss function, whatever you defined, remember that loss function is defined over all the users, right? So in the process of minimizing the loss function, if you were not careful, you could end up minimizing the thing in such a manner that you minimized the loss function for the blue people more at the expense of minimizing the thing for the pink people, because the overall loss function includes both of them together. And there is nothing in the current learning models, unless you're careful, that would guarantee that blue users and red users will have the same risk or loss. And this is the origin of disparate mistreatment. So you could have different amounts of risks for different groups of people. And stripping out the sensitive attributes is just not going to help, because that doesn't solve the fundamental problem here. So what would you need to do if you wanted to avoid disparate mistreatment? Well, you need to have an additional condition, and the additional condition or a constraint is that you would want to insist that the loss for the blue and the pink be the same, right? Another way to formulate this mathematically would be this, that is z equals 0 is blue, say z equals 1, that is the sensitive attribute value is pink, then the probability of actually getting a predicted decision that actually differs from what they should have gotten, which is your chance of getting wrong, should be the same. That's a different way of expressing the constraint, okay? So if you guaranteed this, then you would avoid that. So that's for disparate mistreatment. Let's move on to disparate impact. Why would that come in? Let's go back again to the original figure where blue users, pink users, there is a sensitive attribute, and then there are the non-sensitive attributes, and you're making decisions. Now remember, disparate impact can particularly creep in when your training data is biased. So far we have assumed that training data is unbiased. Let's assume that training data is biased. That means let's change the labels so that the accept and reject labels, so that all the pink users, I've just changed them, so that all the pink users are rejected and all the blue users are actually accepted. Now suppose your training data has these bias labels. Now if you trained a classifier, it will make the biased decisions, and in fact it will use the sensitive attributes to make the biased decisions. So let's now strip out the sensitive attributes in the hope that it would fix the thing, right? Now just stripping these out is not going to remove all the underlying biases, right? The reason is, what any learning algorithm will do at this point is, even after you've stripped out the sensitive attributes, because you've lost some information in the sensitive attributes, the other non-sensitive attributes that are correlated with the sensitive attributes would be given more or less weights, because the learning algorithm, the optimization task, will desperately try to pull back all the missing information, right? So in some sense, the way the learning algorithm will behave is like a very, very determined racist human being who tries to introduce what is called as an indirect discrimination. So indirect discrimination has been observed in human decision making, and it often happens when you have laws that would explicitly prohibit someone from being very discriminatory based on on the sensitive attribute. What you tend to do is you look for other features that are correlated with the sensitive attribute, and you try to get back at them by saying that your decision was based on the non-sensitive attribute, right? In fact, some people argue that some voter ID laws that are being passed in the US states are being pushed deliberately with the intention of pushing down the voter turnouts of certain demographic groups in the US. But because you cannot say, I'm going to push for a law that would lower the voter turnout for African Americans or others, you would actually go at it in a very indirect way. Now, the important thing to understand here is that indirect discrimination is insanely hard to detect, particularly when you do not have the ground truth data, which you don't when the underlying data set has biased labels. And so what have lawyers done, or how do you actually detect indirect discrimination? Now, in the human decision-making scenario, to detect indirect discrimination in the US particularly, and in other places as well, they have this doctrine that is called as a doctrine of disparate impact. And it's been applied in employment and housing practices, and how it works is it applies what I call as proportionality tests over the decision outcomes. That means you look at P1, which is a percentage of people of a particular race or gender who got selected, and you look at P2, which is the percentage of people of another gender or race that get selected, and you look at the ratio between the two, and you would require the ratio to be within a certain bound. So in 70s and 80s, they applied what is called an 80% rule, which is bounding this disparity in outcomes. In fact, in different countries, you use different ways of formulating the rules. Like instead of in the US where you take the ratio, in UK you have P1 minus P2, and in other consequences, in other states or in other laws, you use different ways of capturing the difference between P1 and P2. Now, the fair proportion thresholds, that means this 80% threshold, might actually vary across different domains. 80% was used in employment and housing, but in a different situation, you might use a different threshold. Now, to be fair, the doctrine of disparate impact is a controversial detection policy. The critics would say that there exist scenarios where these disproportional outcomes are justifiable. And the supporters would say there does exist a business necessity clause within the law. That means once you observe disproportional outcomes, the burden is on the decision maker to prove that those disproportional outcomes are justified in some way. But if you could justify, then you're okay. And the other reason for the need for this kind of disparate impact law is because it's necessary to detect indirect discrimination. Just think about it. Without this, it's impossible to flush out indirect discrimination. So let's go back to our origin of disparate impact. The reason why we had this discussion is, so we realized that when the underlying training data is biased, stripping out the sensitive attributes does nothing, or doesn't guarantee that you have removed all the bias, right? So how can you remove the bias further? Well, what we thought was, how about applying proportional outcomes as a constraint, right? Now, keep in mind that we are in a very, very difficult situation. We're admitting that the underlying training data is biased. So in some sense, one could argue that this problem is ill-defined because you're training on some data that you know is biased. So what exactly are we doing here? In some sense, what we're doing is we're trying to make best of a very bad situation where we're thinking that, okay, even though it is biased, there may be something in that data that is worth it. If only we could additionally constrain it in certain ways to at least achieve proportional outcomes. Let's hope that if we did that, we're removing further discrimination that was in the biased data. That's the hope. It's not the best solution, but it's better than not having anything. And in this particular situation, at least you are avoiding disparate impact. And this is particularly useful if you know through some external arguments that in an ideal world, you would have had proportional outcomes. So what would that mean to require proportional outcomes? Well, you can mathematically express it again as another constraint. For blue and red pink users, you would want to have similar proportions of them getting the positive outcome. So to summarize, what we discussed so far are three different notions of discrimination. The first one is disparate treatment. It corresponds to the intuitive direct discrimination. Disparate impact is indirect discrimination when your training data is biased. And disparate mistreatment is actually something that specifically comes up in learning contexts. And there are criterion that you could define to actually avoid each one of them. Okay? So this is good. At least we have computationally understood what the different notions of discrimination are. But now how do we learn to avoid discrimination? Right? Well, at one level, this is ridiculously simple at this point. The idea is to just apply the constraints on the learning. That means, remember, in learning, when you're trying to optimize for accuracy, and now we try to optimize accuracy under those constraints. So in traditional learning, you define the loss function, you minimize this. Now we minimize this subject to certain constraints. And these constraints can simply be the three constraints that we talked about before on the previous slide. This is just minimize this subject to all these three things. And now you're guaranteed to avoid all the three notions of discrimination. It's as simple as that. Now, let me quickly make a couple of observations. The first is there is no free lunch. As you can imagine, every time you apply a constraint on an optimization, you're now minimizing under constraint. So the amount of minimization that you could do for the loss function, which means the amount of accuracy you could get, would keep decreasing. And so there is a direct trade-off between accuracy and discrimination avoidance. Second, you might not need all the constraints, like I put down all the three things, but in certain scenarios, you might need only one or only two. For instance, if you knew that the underlying data is not biased, you can drop the disparate impact constraint. Another thing that is interesting to observe just from the formulation of the thing is if you wanted to achieve only disparate impact or disparate mistreatment, you would actually be better off by dropping the disparate treatment constraint, which is the most intuitive notion that you have, which means sometimes it might, if you wanted to avoid disparate impact or disparate mistreatment, you can do better by actually using the sensitive attribute values and not stripping them out, because it gives you more flexibility in the optimization problem. Now, the key challenge, of course, is we formulated them, but how do we learn them efficiently? So for instance, this is just the formulation with two different constraints, disparate impact and disparate mistreatment. The problem is the moment you add these constraints, at least in this format, the formulations become non-convex. This is the part which is technical, just for a couple of slides. That means you cannot learn them any more efficiently. You can learn this one efficiently, but not this one subject to this. So the trick now, or the game that we play now, is how do we reformulate these constraints in a way that the loss function still remains convex so that we can learn it efficiently. Now, how do we do that? Now, in the next, I think I'm running out of time. So maybe I'll skip the intuition for the reformulation of these constraints. I agree to decrease my talk time for a few minutes, at least, because we're running over. So, so let me just claim, instead of explaining how we reformulate this in a different way. So instead of requiring some equation like that, we have a way of reformulating the constraint where we talk about what we call as, we sort of try to, so this constraint is a disparate impact constraint that says that for blue and the pink users, you would want to get similar proportions of them accepted. Now, instead of that, what we do is we compute a metric which we call as the covariance of the sensitive feature values and their signed distance from the classifier's decision boundary. That means in decision boundary classifiers, typically you have you have every user represented as a point in an n-dimensional feature space. Now we are picking a decision boundary. So we're looking at the people who got selected and we're looking at their distance from the decision boundary. And what we're requiring, what we're measuring, or the way in which we're measuring the sort of disparity in outcomes is by looking at the distances from the decision boundary, and we're computing how they're correlated with the sensitive attribute values. Okay, so maybe with those illustrative examples, it might have been a little bit more clear, but we basically are reformulating that constraint as this one. Now, the reason why we do this is because if you take any, if you take decision, the problem that we had was our earlier formulation with this constraint is non-convex and hard to learn. But then when you change this constraint to this new one, all of a sudden this whole problem again becomes convex. That means you can very easily learn again. So that's the trick. Now, without going into the details, again, a couple of quick observations. It turns out that this way of formulation, our formulation can be applied to a variety of decision boundary classifiers that are out there, whether it is linear, nonlinear SVM, or whether you're using logistic loss or hinge loss. And it works well over a set of, at least the data sets that we tried out on, but there is still, much of the evaluation is still preliminary, and I wouldn't claim big success as yet, but so far it is showing promise. And the one nice thing about the way we formulated our problem is, even though we formulated it as optimized for accuracy under fairness constraints, it turns out that we could actually switch the formulation around to optimize for fairness under accuracy constraints. That means you could also tell that I'm willing to take 10% loss. Now find me the most fair solution. That means the solution that minimizes the disparity in outcomes under those constraints. And that's a nice feature to have, especially if you have situations like business necessity where you might need to have at least certain accuracy. You're willing to give up a certain amount of accuracy, but you want more fairness, kind of a thing. Turns out that this trick that we played for disparate impact can also be applied for disparate mistreatment. These formulations might look like crazily complex, but actually they are not. It's based on the simple idea of like looking at the signed distance from the decision boundary and covariance with sensitive attribute values. So I'll skip over this thing. So to summarize, I was trying to look at discrimination through a computational lens, and what I tried to do was to define three different notions of discrimination: disparate treatment, impact, and mistreatment, and they're applicable in different contexts. And we're trying to propose mechanisms to mitigate each one of them. And the key thing here is to formulate these notions as constraints on learning. It's like you're learning, but you have certain principles or certain boundaries that you're not willing to cross. And we propose measures that can be efficiently learned. And this is the part where the technical magic comes, and this is the part where where we are trying to interpret what those notions might mean in the learning context. So just to encourage people to look into this space, in terms of future work, there is a lot of interesting stuff that needs to be done. Keep in mind that we limited all our analysis to simple binary classifiers. We still have to extend our definitions or notions of discrimination to multi-class classification. Turns out that this is non-trivial. We'll have to think about what do these notions mean in regression tasks. What do these notions mean in set selection? Set selection is something that you would care about if you're talking about recommender systems. And what does it mean to be non-discriminatory in ranking. Ranking is something that you would care about every time you're doing a search. Now, again, even if we did this, we're still limited ourselves to discrimination, and fairness is a much broader topic than discrimination. To just give you a quick feel, consider recidivism risk prediction tools that are often being discussed today. Oftentimes, these tools use a number of different features to predict somebody's risk, and they use features like personal criminal history, family criminality, work and social environment, and all these kinds of features. Now, is using somebody's family criminality, that means whether they have friends and family members who have prior criminal record, is using that for risk prediction fair? Many of us might think that it is unfair. But then how do you come up with a measure of the social community's sense of fairness of using this feature in decision making? Because family criminality is not a socially salient group. So it's not protected by default by the anti-discrimination laws. But this has more deeper implications for fairness. And how do we account for such fairness measures when we are making decisions? This sort of a feeling that we have about, because of our cultural, social, political, or privacy laws or whatever, we have certain discomfort with using certain features in decision making. Now, how do we capture those, and how do we account for them when we're making decisions? Now, this is some work that we recently started working on, and we have a preliminary attempt at tackling this particular problem at a paper that we published recently at the ML and Law workshop at NIPS. Now, beyond fairness, which is the focus of this talk, there are all these things about accountability, transparency, and explainability that prior speakers have done a much better task of explaining those things. So with that, I'm going to stop. I have the last few slides, which are like references for our works and a lot of interesting work that has been done in the recent years by a number of other groups. And I would highly encourage you guys to check those things out.